Okay, thank you, Nicholas, for inviting me. So my plan was to arrive on Monday, but unfortunately, due to the weather conditions, my flight was canceled, and then it was very difficult to find alternative flights because everyone was in the same situation, and all the flights got booked very quickly. So unfortunately, I had to arrive yesterday evening, and so I will be here for today and Friday, and actually I return on Saturday. So if you want to have any discussions related to my talk or anything in general, I'm here until Saturday. So today I will be talking about AI-related work that I'm doing. Originally, I work in the field of high-performance computing. I've been doing GPU programming since maybe 2007, right after CUDA was released and GPUs became programmable. But more recently, I've been moving more and more towards the AI-related work for a few reasons. I submit proposals to a bunch of different, on a bunch of different topics, some related to linear algebra, HPC, and some related to AI. And guess which ones get funded, right? So then I have to work on the things I get funded for. So naturally, I have been transitioning towards AI at the intersection of AI and HPC. And today's talk is one of my recent efforts in this regard. So as an introduction to our university, so Tokyo Tech is one of the leading institutions in Japan. And we actually introduced the first GPU supercomputer about 20 years ago. Or sorry, not 20, more like 15 years ago. The person who introduced it is sitting right there. Satoshi Matsuoka is the architect of Tsubame, which was one of the early adopters of GPUs. And of course, as you know, GPUs have become essential for the training of large deep neural networks. And if you look at, is this a laser pointer? I wonder, oh, it is, okay. But it's a little bit hard to see. Maybe I'll just use my mouse. Or sorry, it's not showing. So as you know, the size of these deep neural networks have been increasing at an exponential scale. And when I say exponential, it's a little bit faster than the Moore's law kind of exponential, because if you look at 1 year, the sizes are increasing like roughly an order of magnitude each year if you look at the slope in this in this semi-log scale plot. And models like GPT-3 were considered large a while ago. Now you have these things that are like 3 orders of magnitude larger. Of course, some of them are just like stunt models that don't actually are not used in production, but some are, right? Things like Palm or Switch Transformer, Megatron. These are actual models that are used in production. And so, of course, this kind of increase is not sustainable, but it gives you an idea of, now these models are not trainable without GPU supercompute. Well, not necessarily GPUs, but they require supercomputers. Okay, and it's not just getting larger. There's some benefits to scale. And there's this famous scaling laws paper, and also its counterpart in Vision. And so the original scaling laws paper came out for natural language modeling. And in this case, if you increase the compute or dataset size or the number of parameters exponentially, you get this power law scaling of the improvement in the test loss, or the same thing in accuracy, depending on what you're measuring. But in any case, The larger the model, the higher accuracy you get. And also, this sort of incremental improvement in accuracy is not the only benefit. Now, there are many studies that show a sudden increase in capability, things that were not possible in the smaller data sets and smaller models suddenly become available. These new features are acquired by these large models by increasing the scale beyond a certain point. And of course, when you apply this to vision, you see a similar trend, but what the original vision transformer paper shows is that just making the model larger without changing the size of the data set does not necessarily give you better accuracy. And similarly, if you only increase the size of the data set that you're pre-training on, it doesn't necessarily lead to a better accuracy if you don't increase the size of your model. So large models alone do not lead to better results, and larger data alone do not lead to better results. We need to increase both the size of the model and the data set we use to train it on. However, a big problem in the vision field is that unlike natural language processing, where abundant data is available, the larger data sets are owned by Google and are not made available publicly. And so that's a big problem that even if you have a supercomputer, even if you have enough compute resources, you simply cannot compete without this large data set. And so there's an effort to create large open data sets that are even larger than JFT. But then what is the way to train these when at scale? So these data sets like CFAR and ImageNet are fine at small scale. Like ImageNet is considered very small in like modern standards. But when you try to scale this to like billions of images, you'll end up classifying these into like 1 million different categories because of the sheer size of the data set, the number of things that are in them, and the number of categories also increases. But does it really make sense to keep doing classification at that scale? If you're sort of measuring these histograms as output, and it says, it gives you a number for each class. If you have 1 million classes, that's really not how people do this, right? When you look at an image, it doesn't go through the 1 million bins and tries to determine which one is the actual category that it belongs to. And so there's a limit to scale at which this classification paradigm makes sense. And so we are gradually moving away from just simple classification as a sort of training methodology. People are moving towards vision and language models, which train on the text that describes the image, so it's not really tied to one label, right? It's not supervision in that sense. It's more about aligning the text data that comes in and the image data that comes in. They're both encoded into their representative formats, and what image corresponds to what text is what is learned. And this scales because you can find explanations of images. If you like Google for some keyword, then you get image, and you can scrape the web for a bunch of image text pairs, which is what creates this kind of large open data set. So there's this movement towards moving to more scalable training methodologies, and this is the fruits of this kind of training you're seeing already with things like Stable Diffusion. You input whatever description you want, and it outputs an image. The implications of this kind of new sort of model of training are huge. For example, these things were considered black box, but if you consider the fact that these things are now aligned with text, you can actually talk to your model. Like think of ChatGPT. You're actually talking to your model, and what it learned is not necessarily just the language itself. It learned the images with them, or if you feed in scientific data with the text, it actually learns the scientific data along with the text, and so it can talk to you about what it thinks it learned, right? This is a whole new method to make your model more explainable. If you can talk to it, of course, you can learn a lot from what it thinks it knows. And this is already happening on the language side. The multimodal aspect needs a little bit more work, but I'm sure this is going to get there quite soon. And so training with these both modalities is very important. Things like CLIP use this kind of contrastive pre-training. This is one of the early examples of what, the one that says ours is the work that first described this. What the task is, given a text like this, it tries to produce an image that best describes what's written in this text. These old GAN models, they did a horrible job, as you can see here, in describing these things. And one of the early attempts to do this through CLIP was also not so great, right? The ones that you see now are much more high resolution and have much more detail, right? So things like Glide, DALI, Imagen, Party, these, given very complex text, they can actually show you pictures, very detailed pictures of these imaginary situations. And this is possible because you're aligning text with vision models, and you're using sort of these sequential denoising models that do much better at high resolution. And they don't have the weakness of GANs for being very difficult to optimize. So now we are moving into a new era of being able to actually talk to your model and then have the model output things from the text that you input, right? So it can turn language into actual images or things that you want it to output. Okay, going back to the scale of these things. So if you look at the size of the models that are required to output such nice images, some are in the orders of tens of billions of parameters. And also, the data set size to train them on is in the order of billions. Okay, and so the only people who can train such large models there are only a handful of people, mainly in industry, that can afford to train these large models. But what about people in academia or just researchers? And we know we have like allocations on supercomputers, so who is trying to do this, right? So I'm involved in one of these efforts from the academia side to actually try to compete with these large industries, because things like INCITE award like millions of GPU hours per year, and that is sort of comparable to what the industry is using to train these large models at the moment. Okay, and so this is an INCITE project that is focusing purely on like AI, right? Usually INCITE has a proposal with some component of machine learning, but it mostly focuses on scientific projects. But this one is a pure AI project. And so there are efforts to train these large models using our HPC resources. And the two main topics that we want to train on is first, the GPT NeoX is a variant of GPT, a language model. OpenClip is a thing that I've been describing, which takes in both text and images. and tries to train that. And so we want to train this at very large scale. Of course, these things, when you use data parallelism, they scale very well onto large number of GPUs. However, so I'm now transitioning to the main topic of today's talk. Even if we can get these large vision and text data sets, we still have some fundamental issues. At this scale, you cannot manually label or clean your data, and the cleaning side is the bigger problem. Because labeling, you can get around through self-supervised learning nowadays, and like I said, these methods are trained in a different way. They don't necessarily have labels. They have corresponding text that are paired to the images. And so it doesn't really require that traditional kind of supervision anymore. However, the following issues are quite serious, even for these types of data sets. So because these huge data sets are done by scraping the internet, obviously there are privacy, copyright issues, and there's a whole bunch of different biases that are found on the internet. And at this scale, it's very difficult to clean. And also, efforts to try to manually clean this through like cloud sourcing also have resulted in some ethical issues of exploiting cheap labor to actually do that. And so this remains a sort of multiple problem in just simply trying to create clean data sets. And if we can't train these large models on clean data sets, then it's going to be cause a huge number of problems downstream. And also, at this scale, it's already impossible to download these data sets. The hugest ones take weeks or maybe months if you try to download them from sites in other countries. And we don't really have a nice sort of web caching framework or like mirrored sites all over the globe yet for these huge data sets. And just simply moving around petabytes of data over different continents is not going to be that fast. Also, if we start including scientific data, those are even larger than just simple language or image data sets. And so basically the bandwidth is not keeping up, and I don't see it a sudden increase in the near future. So this is going to be one of the major bottlenecks. Okay, so cleaning and downloading these data sets is going to prevent us from actually achieving much more progress in this area if we don't have any alternatives. And so that's why I'm interested in synthetic data sets. And by synthetic, I mean, it doesn't come from real images or actual real stuff that's on the internet. So in that case, because they're purely synthetic, you can make them as clean and unbiased as they come. There's no copyright or privacy issues because it doesn't actually include any real data. And you can generate, because they're synthetic, they're generated, you can generate them locally in a reproducible way. So there's no need to download such data, right? So all these issues with real data are actually mitigated through training on synthetic data. The real question is, how good can you train on synthetic data, right? Like you're trying to learn information about the real world, and it's sort of doesn't make much sense if you are trying to learn from the synthetic world about the real world, right? So why is this possible, and how well does it work? So one of the things we tried is try to create these fractal images from very simple equations that generate these complex patterns. Okay, so the equations themselves are very simple, but the patterns they produce are very complex. That's the nature of fractals. And some preliminary experiments where you compare training on a real data set, which is shown in this purple, and training on the synthetic data set, shown in the pink line here, show very close results when you measure the downstream accuracy. So this is done by pre-training on these data sets. And there's actually a fine-tuning phase where you actually fine-tune on real data sets. Okay? So it's not like we're doing zero-shot from only synthetic images. There's a mix of real data sets in there. However, once you pre-train on these large synthetic data sets, the amount of data used for fine-tuning is very small. Therefore, you can afford to clean that small fine-tuning data set. Right? So it removes this problem of having to clean this huge data set. The amount of data that you need to clean is affordable if you just need to use it for fine-tuning. So that's why it makes sense to have a huge data set for pre-training that is purely synthetic. And so these preliminary experiments were done at ImageNet scale. Right? That's about roughly 1 million images. What we really want to do is to do this at like a 3 billion image scale. So there's a 3,000 times increase in the amount of data that we really want to use this for. And to achieve this, we've had to go through different problems. One of them was at this scale, there's a lot of I/O issues. One is it sort of exhausts the number of inodes on these supercomputers. So at the time, we were using the ABCI supercomputers that have about 4,000 GPUs. But when we tried to store things in the traditional way, meaning each image is stored separately in a folder that represents the class, when we tried to read in like 50 million images at a time, the training simply didn't start, even when we waited for like 3 hours. And so it was putting a huge strain on the file system. I think the other users were wondering what was happening to the machine when we were doing this. So you have to move to this different kind of model where you basically store things in big tar files, like a million, or not a million, like 10,000 images in one tar file, and you sort of distribute these tar files to each node, store it in their local SSD, and you sort of do away with global shuffling because at large scale, you have enough local data that after the all reduce, you can sort of mimic global shuffling by choosing locally which data to use. And so now it's quite common to use these frameworks like web datasets where you just read from large local tar files without global shuffling. Also, there were other technical challenges upon scaling up these synthetic datasets. So we tried to figure out what kind of synthetic dataset or what kind of pattern, primitive pattern, gives the best pre-training effect. We tweaked a bunch of hyperparameters when creating these datasets. So this is basically a lot of hyperparameter tuning. How many vertices to use, how many number of points we use to render these images. And these are all hyperparameters, but the good thing about tuning hyperparameters in your dataset is once you have a good dataset, all the models that use that good dataset benefit from it. It's not like hyperparameters for your model where for each dataset you need to sort of retrain the hyperparameters. In the case of the dataset hyperparameters, they just simply create a good dataset. And once you do that, it's generally useful for any model. Okay, so in terms of the scores that we're getting, so this VIT tiny and VIT base are typical vision transformers that people use these days. They're on the smaller end, but we first started out small. So a data set that we used for reference is ImageNet 21K. This is different from ImageNet 1K, which does a 1,000 class classification. This is a 21,000 class classification. It's about an order of magnitude larger than the original data set, the ImageNet data set. But compared to the pre-training on that medium size real data set, we get better downstream accuracy. The downstream task is ImageNet 1K. So actually, pre-training on ImageNet 21K and transferring that to ImageNet 1K is a much easier task because they're sort of almost in the same domain. We are pre-training on an entirely different domain, which is synthetic data sets, and yet we are getting superior accuracy on the downstream ImageNet 1K task, and which is very surprising, right? Why would this happen? Why can you use a completely synthetic image and get even better accuracy than training on a larger ImageNet? So we've tried to see how large we can go, and so we increase the number of classes from 21K to 50K and even 100K, and try to make the data set size larger. There are different configurations here. N is the image size when doing the fine-tuning. This is the batch size, learning rate, and the number of epochs we trained on. The highest score we got was 83.7, which I think is, yeah, this one, which is very close to the score of pre-training on this private data set owned by Google. Their score is 84.2, so we're about 0.5% away from this data set. So if we can keep training larger and larger synthetic data sets, one day we might surpass this one of the largest real data sets. The good thing about synthetic data sets is that unlike real data sets, which are static, you can increase their quantity but not their quality, right? You can't really change what's in them. But our synthetic data sets, we can generate whatever we want. And so as we tune the hyperparameters more and more, the quality of the images and in this data set keep improving. And so it's only a matter of time until it exceeds real data sets. OK, so the real question is, why does this work so well? So one important thing to clarify here is that we are only using these synthetic data sets for the pre-training. So there's two stages. We first pre-train these large models with huge data sets, and then we fine-tune them on the actual problem that we're interested in. And these synthetic data sets are used only for the pre-training, but this is where we have all these issues with cleaning the data, because the data set required for pre-training is huge. And that part we think can be done with synthetic data. If you think, I don't know if this is a good analogy, but humans, when they're born, they haven't really trained their visual cortex on any real data, yet we are sort of ready to take in all this data. You can think of the pre-training as something that happens before you're born, and the fine-tuning as something that happens after, right? You actually get real data, but your visual cortex or your nervous system is formed before that. Also, what's actually happening, this is a hypothesis, I think the lower layers, like close to the input, are known to learn the local features, not the semantics of these higher level features, but shapes, basic shapes, curves, edges, contour lines. These basic geometric shapes are being learned. And with the rich local features, you can build your vision model on top of them. And I think these synthetic images are providing a huge amount of data to train these local features on. And semantics are dealt with at higher layers, which probably are trained during the fine-tuning. Some advantages of synthetic data sets, just to go over them again, are they can be improved continuously, right? This is a huge difference from real data sets, which are, can only be increased by quantity. You can actually increase the quality of your data set if you can generate whatever you want. While real data sets are static and can only increase in quantity. Also, if you are interested in a certain aspect of your data, for real data sets, you can't really change just one part of it. You can't really change what's in the picture. But for these synthetic data sets, you can tweak one of the parameters to see, like, what is the important part of your data set? Like, is it the brightness or, like the complexity of the contour lines? You can change one aspect and do a systematic investigation. You can probe your data and see what actually matters for the training. And therefore, it's much easier to investigate what actually, makes a good data set if you're using synthetic ones. Okay, so I don't know if I have more time. I think this is my last slide. So yeah, thank you very much. This is the end of my talk.